Hello Bearcats! We will review and look at the details of parent or base functions in this lesson. First, let's take a look at linear functions. The base function would be y equals x or f of x equals x. Our base function, our base function graph would be, of course, at the origin and then with a slope of 1. And of course, that is kind of off. Sorry about that. With a slope of 1. A couple of things that we want to note about this is that our domain would be a set of all real numbers, which would be negative to positive infinity, soft brackets. The range would also be all real numbers, negative to positive infinity, with a soft bracket. The other thing that I want to note is that this graph moving from left to right is moving upward. So it is increasing on an interval from negative to positive infinity. Next, I want to talk to you about the constant function. The constant function, or the identity function, has a slope of 0. And you should note any time that there's a slope of 0, it's a horizontal line crossing the y-axis. So it'll be a y equals equation. And so if we draw our y value or cross our y value at 3 or 4, can't look, we'll say it's 3. We'll say y equals 3 would be your equation for that particular. Our range would be 3. And it'd be a hard bracket because it would be constant. It would always be 3. Y would always be 3. The domain would be negative to positive infinity. All right, while we're talking about lines, let's go back to an example that you're going to see from time to time. What if you're given information like this? You're given f of 1 equals 3 and f of 4 equals 0. All right, what you want to glean from this and look at this and know is that you have a set of ordered pairs. The x value is 1 and the output is 3, so you have an ordered pair 1, 3, and another ordered pair 4, 0. All right, let's go ahead and write the equation in point-slope form. First, we need a slope and a point. We have a couple of points. We'll use the first point. We're going to take this one as x1, y1, and this is x2, y2. Our slope, of course, would be y2, which is 0, minus y1 is 3, over x2, which is 4, minus 1. We're going to get a slope of negative 3 over 3, which is negative 1. That is our slope. And we're going to use the first ordered pair and write it in point-slope form. So we're going to write y minus 3 equals our slope of negative 1 times x minus 1. And that would be something that you might see coming up. All right, let's go on to quadratics. Our quadratic base graph is f of x equals x squared. We could create a t-table to get us some values to remind ourselves what that picture looks like. We're going to use negative 2, negative 1, 0, 1, and 2. If we square negative 2, we would get a positive 4. Negative 1, we would get a 1, 0, 1, and 4. Our base graph would look something like this. We would have, of course, the ordered pair at the origin, a positive 1, 1, and a positive 2, 4. 1, 2, 3, 4. And then over here on the left, negative 1, 1, and negative 2, 4. 1, 2, 3, 4. And our graph would look something like this. I didn't do a very good job. Sorry about that. You know a parabola with a vertex at the origin that's turning upward would be symmetrical with the y-axis. So it has y-axis symmetry. Because it has y-axis symmetry, it is an even function. We also know that the domain would be all real numbers, or negative to positive infinity. And the range in this case would be from 0 to positive infinity. It's equal at 0, so you're going to use a hard bracket to positive infinity. And there's our quadratics. Let's move on to cubics. For our cubic function, again, we're going to create a t-table. And we're still going to use the values of negative 2, negative 1, 0, 1, and 2. And when we cube negative 2, we're going to get a negative 8. When we cube negative 1, we're going to get a negative 1, a 0, a 1, and a positive 8. All right, when we plot those points, we would have, again, at the origin, and then we would have 1, 1, and we would have 2, positive 8. And on the left, we have a negative 1, negative 1, and then we have a negative 2, negative 8. And your cubic graph would look something like this. All right, let's take note of a few attributes of our cubic graph. This cubic graph has origin symmetry. Therefore, it's an odd function. Also, it's got a cubic, so 3 is an odd number. When you move from left to right, the function continues to increase. So as you move to the left, from left to right, the function is moving upward. So it increases on the interval from negative to positive infinity. I think that's about all we know. All right, let's move on to square root. You can pause it anytime you'd like. All right, when we get to square root, again, we're going to create a t-table, but we're going to have to notice some things. One, that's one of our big red flags for restrictions. We know we can't have a negative under a square root, but we do know we can have a 0. So when we take the square root of 0, we get 0. We take the square root of 1, we get 1. I'm going to be really careful in the numbers I choose for my table. I would pick 4 because the square root of 4 would be 2, and then I would pick 9 because the square root of 9 would be 3. So there's our t-table. To sketch our graph, we would be at 0, 0, and then we would be at 1, 1, and we would be at 1, 2, 3, 4, 2, and at 9, which would be way up here off the graph, at 1, 2, 3. And our graph would look something like that. All right, there is no symmetry in this graph, and it's neither an odd nor even function. But as our graph moves off to the right, it is increasing, so it would be increasing, and this time on an interval from 0 to positive infinity. When you talk about intervals for increasing and decreasing, you're going to use just soft brackets, and that can be a little bit conflicting with interval notation, so try to pay attention to that. This is about increasing and decreasing intervals. And then last, our domain. Our domain would be all numbers greater than 0, so from 0, equal at 0, so hard bracket, to positive infinity, and our range would also be from 0 to positive infinity. All right, 2 more to go. Let's go on to reciprocal functions. Reciprocal are rational in functions. It's what you knew it from Algebra 2. And let's take a look at a t-table for this. If we pick negative 2 and we plug it in, we would get a negative 1/2. A negative 1 would yield us a negative 1. A 0, ooh, we have to stop. Can't divide by 0. It's a restriction. That would be undefined because it would be an asymptote. All right, so our x value at 0 is undefined at 0. Then if we pick 1, we would have positive 1, and if we pick 2, we'd have positive 1/2. If you remember, these have 2 branches, and they look something like this. So we'd have this point, and you would have this point, and your graph would hug the asymptote. So there would also be an asymptote at the y-axis, and you would have this point, and your graph would hug the asymptote here as well. That's our base function for rational functions. If we look at this, it has origin symmetry. If I were to draw that XY line and fold it, you would fold on top of it. So it has origin symmetry. And it's an odd function. And as you move from left to right, the graph is constantly always decreasing. As you move, it's going down here. And as you move from left to right, it's going down here. So it's decreasing on the interval negative infinity to 0, and then we have to write another interval from 0 to positive infinity because we aren't equal at 0. Domain would be again from negative infinity to 0, not equal at 0, and then again, or would start up at 0 and go to positive infinity. And the same with your range. So your range would be written as negative infinity to 0 or from 0 to positive infinity. This is all review from last year. All right, the next thing we do is not review. We're going to talk about a special type of piecewise function called a step function. A A step function is also referred to as the greatest integer function sometimes, and what that means is it is the greatest integer. This is a definition of greatest integer. The greatest integer less than or equal to x. All right, and we'll talk a little bit about that after we get the parent graph down or the base graph down. The function looks like this, f of x equals, and it's this little double bracket, and I don't draw very good, but it's a little double bracket, and that is the greatest integer function. There's a really great picture of all these graphs on page 70 in your textbook. You might want to take a look. It'll probably look a lot better than mine. We're going to go ahead and graph what it looks like, and it's really hard in this little bitty graph, but you're going to be at the origin, and you move constant to 1, and you have an open dot, and then you move up, you step up, and you go over, and you have an open dot, and I'm way off on this, so sorry. So you should go here, and it should go to there, and it should go here, and should just go to there, and I'm off a little bit. Like I said, page 70, the picture looks much nicer, and it would go the opposite way too. So this would be open, and this would be closed, and this would be open. Oh, I can't do that. Open and closed and open and closed, and it would look something like that. Page 70, much better. All right, want to talk about the domain. Because there's a closed dot above the open dot, then there is not a break in your x values, so the domain is negative to positive infinity. The range are all integers because they step up each integer. They jump up. So all integers. All right, one last thing I want to talk about greatest integer function, just algebraically when you have to calculate that. Think about this. If I had a number line, and there is 0, and there is 1 and 2, and negative 1 and negative 2, and I ask you to find the greatest integer, the value of the greatest integer at negative 1.3. Or I ask you to find the greatest integer value at 1.3. And I want to talk about this. It is the greatest integer that is less than. That means you have to always look or move toward the left. So if I'm at negative 1.3, then if I move to the left, my greatest integer to the left would be negative 2. So the output here would be negative 2. If I am at 1.3 here and I move to the left, my greatest integer to the left of that would be 1. And that would be my output. All right, that's it. I will see you tomorrow.